Okay, last time we talked about angular momentum, and today I want to introduce the concept of work. So basically, the work the work done by a force on a particle is defined by W12, which is the integral from the point 1 to the point 2 f dot ds. So the way to imagine this is to basically we have a coordinate system x and y, and we have a certain particle, and on this particle acts a certain force f, and it moves in a certain direction ds, right? So so what we have to do, actually we have to write this f dot ds like this, right? Because this is the dot product. So so the work done is basically the dot product between f and ds, and then we integrate this from the 2 points 1 to 2. So if this is the point 1, and then this goes along a certain trajectory like this maybe, and this is the point 2, what we have to do is we have to take each of these points, and here and here and here, we have to take each of these points and sum the dot products between the f and the ds up to get the total work done. And so this is when you have discrete amounts of when you have discrete steps, and if you take the limit as the time tends to 0, as the differences in time tends to 0, then it becomes an integral, right? So let us recapitulate what the force is. The force is equals to d by dt of m times v, right? So we can use this formula and plug this into the formula for the work. So we take this and plug it in here. Then we have the integral from 1 to 2 d by dt m times v dot ds, right? And now this is the same thing. We are assuming that the mass is constant. So if we differentiate m times v, the constant just falls out. So this becomes m times the integral from 1 to 2. And then we have dv by dt dot ds. And now the interesting thing is ds is actually just v dot dt, right? Because ds is the displacement. ds is the displacement of the particle, and the particle is basically just the instantaneous velocity times an infinitesimal time period, right? dt, right? So we can write this as m, the integral from 1 to 2 dv by dt v dot ds, v dot dt, right? v dot dt. Okay, v dot dt. And now this is the same thing as m, the integral from 1 to 2 d by dt v squared half dt. Why is that? Let us try it out. If we differentiate v squared over 2, then we get basically 2 times v half times dv by dt. So the 2's cancel, and then you get dv by dt times v. So this is correct. This is correct. So, and now we have a total derivative, and we're differentiating with respect to t and integrating with respect to t. So this just becomes m times v squared half between the points 2 and 1. So that's just m v2 squared half minus m v1 squared half. And now this is just the change in kinetic energy. That's what we call it. So so this gives us the definition of the kinetic energy. The kinetic energy of a body is just m times v squared half, right? And T stands for kinetic energy. But you see that this quantity is always Yeah, so this is the change in kinetic energy. When we've defined the kinetic energy, it will be mv squared half. Notice that we have assumed that m is a constant. If m is not a constant, then the analysis becomes a bit more difficult. But we in classical mechanics we usually assume that the mass is constant. So the work done between 2 points by a external force F acting on a particle of mass m is given by the differences of the kinetic energy from the end and subtract from that the beginning kinetic energy. So yeah, that's it. Next we're going to take a look at what a conservative force is, and yeah, okay, thanks for watching. Bye.